Right. Thank you. Thanks to the organizers for this opportunity. I'll be presenting some work I did with the collaborator Vishnu, who's at Okinawa Institute in Japan right now. And we wrote this paper in JPO last year explaining how a flow transitions from asymptotically small to order one Rossby numbers. So here's some background on wave balance exchanges in the small Rossby limit. Quite a lot of data sets have come up across ocean models, satellite altimeter data sets, and in situ measurements, and all these point towards the paradigm that internal waves in the ocean in general can be of a varying strength in comparison to the balanced flow. There are regions in the ocean where waves are significantly energetic than balanced flow, and there are regions in the ocean where waves are much weaker than balanced flow. And quite a lot of theoretical and numerical work has gone into understanding how these different kinds of waves influence balance dynamic in the small Rossby limit. And we can get some insight based on asymptotic analysis of these interactions in the small Rossby limit. So this is a nice equation that's derived by Wagner and Eng. And plotted, this is, it's an equation like QG. So the black terms are QG-like terms, but the red terms that you see here are the terms that appear due to nonlinear wave interaction. So, and this is specifically in the regime where waves and balance flow energies are related by this expression. So balance to wave energy ratio is order Rossby square. So when Rossby number is, say for example, if it's Rossby number 0.1, a balanced energy is 100 times less than wave energy. So you need a lot of waves or high energy waves to significantly change balance dynamics, as Rossby number is an asymptotically small parameter. So this is a figure from a paper we wrote with the collaborator. It's plotting the geostrophic vorticity field for two regimes. This is a geostrophic vorticity field for balance and waves of comparable strength, and this is when balance flow is or Rossby square wave energy. So its balance is much weaker here compared to here, and you can see how these large-scale coherent structures form as in QG dynamics in this regime, whereas when waves are much stronger, they can destroy a lot of these coherent structures and dissipate them at small scales with a forward cascade. So as wave energy is much higher than balanced energy, there's a forward cascade and significant dissipation of balanced energy in the small Rossby limit. So that's one of the punchlines of all these papers in general. If you read and look at them in detail, you really need a lot of waves in the small Rossby limit to cause damage to the balanced flow structures. For this particular work that I'm describing, we decided to look at what happens as flow Rossby number transitions from small to order one regime. And this is inspired by, again, a lot of observations in the ocean that point out that high energy regions, high eddy kinetic energy regions that have Gulf Stream, Kuroshio, weakly sheared eddies in the mixed layer, and also when these eddies interact with the bottom topographic regions, these are situations where you can locally excite order one Rossby number flows, and these flows often interact very violently with inertial waves or inertial oscillations. So excite a lot of inertial oscillations or inertial waves in the ocean when you have atmospheric winds blowing over the ocean as a result of eddy topography interactions, or also as a result of spontaneous generation. So a lot of these mechanisms, eddy topography interaction, spontaneous generation, they all excite internal gravity waves. But if you look at the internal gravity wave spectrum that has frequencies going from the inertial frequency F to the buoyancy frequency N, inertial frequency is the lowest frequency in the wave spectrum. So all these mechanisms, spontaneous generation, eddy topography, they all end up exciting a lot of waves in the low frequency end, which end up being inertial waves or inertial oscillations. And these can interact with these order one Rossby number flows in different dynamic regions in the ocean. So we decided to look at this interaction using an idealized model. So we're thinking of a situation where we have an order one or high energy barotropic flow. So the schematic is shown here. We have an order one high energy barotropic flow, and we have a low energy high barophilic flow. So a lot of times these interactions excite waves which are not often very, very energetic. The wave energy levels can be pretty small, especially in spontaneous generation or eddy topography interactions. You still have an order one high energy eddy field interacting with a very weak unbalanced flow. So we think of the barotropic flow as a proxy for an energetic balanced flow, and high baroclonic mode, this is the mode that contains inertial waves or inertial oscillations. And we're trying to understand how these two interact, especially at order one Rossby numbers. And so this is also representative of a typical situation in the ocean where if you look at the vertical mode energy distribution, most of the energy in general is contained in the barotropic flow and the first couple of barophilic modes. The energy levels decrease significantly as you go to high baroclinic mode. So it's a situation that we're trying to mimic in a reduced model. And we get this model by projecting the primitive equations on barotropic and a single high baroclinic mode. So that ends up giving us a model that looks like this. So here's the reduced model. So we have evolution equation for the barotropic vorticity, zeta t, and these are the equations for the baroclinic velocity and pressure. And these equations, so we're forcing these equations with an external term, Ft and Fc, and there's dissipative terms added to take out energy accumulating, to prevent energy accumulated grid scale. And the forcing in the baroclinic term, the baroclinic forcing specifically excites inertial oscillations or inertial waves. And we're trying to understand how these two interact. So we numerically integrated this model across Rossby numbers. Rossby number changes from small to order 1 values. We ran about 100 numerical integrations, and we got about 77 cases where the flow reached steady state, forced dissipative equilibrium in reasonably short time scales. So this plotted here is the energy level of the barotropic flow. So that's red ones. These are barotropic energy levels, and the blue is baroclinic energy level. So baroclinic energy levels are about 10% of the barotropic energy level across all Rossby numbers. So we force the system and end up getting a series of these experimental flows, and we are studying how these the characteristic features of these flows look across Rossby numbers. Here you can see on the left column the barotropic vorticity field, and the right column is the baroclinic velocity. You can see the barotropic flow at low Rossby number. So R01 is the lowest Rossby number, and R03 is the highest Rossby number. So we're moving from low to high Rossby numbers. At the lowest Rossby number, we see more or less the same number of positive and negative vortices, cyclones and anticyclones, and these are domain scale big coherent structures. Whereas as you go to order 1 Rossby numbers, we see that these negative vortices, due to many instabilities, they break up, they form a background soup, and these positive vortices, they reduce in number and size, and they're sort of coherent at the small scale. So the size is reduced. That's the main observation, the barotropic vorticity field in the left. The baroclinic field, this is the baroclinic magnitude of the baroclinic velocity. So you can see here that at the lower Rossby number, we see these big structures, whereas as you go to order 1 Rossby number, the structures again break down, they become much smaller scales with a lot of dissipation. So both these fields are highly dissipating at order 1 Rossby numbers. These are showing us the spectrum, the energy spectrum of barotropic and baroclinic flow. Barotropic flow, especially, you can see it at the lowest Rossby number, R01, it's this red curve. It's a pretty steep spectrum. It's close to -3, whereas as we increase Rossby number, it becomes shallower and it approaches more of a -5/3 limit. Baroclinic spectrum does something similar. It's relatively steep at low Rossby, and it becomes shallower as we increase Rossby number to our own values. And looking at the spectrum, you can actually notice the difference. You know, the energy levels at the larger scales are much higher for the barotropic flow compared to the baroclinic flow. So barotropic flow is significantly more energetic than baroclinic flow. And yet, you know, the surprise here is that this baroclinic flow is very low energy level, and yet it can impact the barotropic flow significantly as we increase the Rossby number to our own values. Plotted here is the histogram of the barotropic vorticity field across Rossby numbers. So this is again something that's observed in the ocean and also seen in a lot of these regional ocean model studies. The vorticity field is symmetric with more or less equal distribution of cyclones and anticyclones at low Rossby number. That's this red curve. But as in increase Rossby number, there's a significant asymmetry with positive vortices taking higher values and negative vortices, the RMS, decreasing as Rossby number is increased. Another feature that's again observed in ocean models and has some interesting theoretical predictions with idealized models is the affinity for near inertial waves and anticyclonic vortices. So at low Rossby numbers, here if you look at these two fields, if you compare them, these red thick blobs that you see, these are pretty strong in regions where there's an anticyclone or negative vortex. So these high baroclinic energy levels at low Rossby regime is strongly correlated with negative vortex regions. So that's what we see here. And so plotted here is the correlation between barotropic vorticity and baroclinic energy. When you plot this across Rossby numbers, at low Rossby numbers, the correlation is negative, which indicates its affinity for anticyclonic vortices for the baroclinic flow. But as we increase Rossby number and it reaches order 1 value, these negative vortices disintegrates in the barotropic flow, and the affinity is lost. So this, we don't see any correlation as Rossby number approaches 1 for the paraclinic flow with the negative barotropic vorticity field. So these are showing us the energy fluxes of the barotropic and baroclinic flows. Barotropic flow, so the red curve again is the energy flux for the lowest Rossby number case, black is for the highest one. So as we increase Rossby number, the flow gets a forward flux whose magnitude increases with Rossby number. There's a gradual monotonic increase in the forward flux. So there's it's pretty much an inverse flux at the lowest Rossby number, but it gradually transitions to a forward flux as we increase Rossby number. And this is showing us the baroclinic energy flux. This also monotonically increases with increasing Rossby number. And with this increasing flux, energy flux, the dissipation also monotonically increases. So plotted here is the dissipation of barotropic and baroclinic flow. So red is the barotropic energy dissipation, blue is the baroclinic dissipation, and the black is the sum, the total dissipation, which equals the rate of energy injection in the system. So all these quantities monotonically increase with Rossby number, along with this increase in magnitude of the forward flux of the flow. And if you really stare at this figure, you will find that the flux is negative at the lowest wave number. So this is K1, K0 is somewhere here. Barotropic flow, the flux is negative at the lowest wave number, which means barotropic flow is on average losing energy. And it's positive for the baroclinic flux, which means baroclinic flow is gaining energy. So there's an energy transfer from the barotropic flow to the baroclinic flow, and the magnitude of this energy transfer increases again monotonically with Rossby number. So as at the highest Rossby number, there's a significant amount of transfer from barotropic to baroclinic flow as a function of Rossby number. So the given that this flux is positive, so this is something that's that we found very interesting to locate regions in physical space where this forward flux is high. So in general, so if we have a field psi, so assume psi is some field, we can filter this. We introduce a high pass filter. So psi tilde is a Fourier truncation of psi retaining high wave numbers or small scales. So psi tilde is a high pass filtered version of the original field psi that maintains small scale structures. We can high pass filter the whole governing equation, the equations we are using, and we can write an equation of this form where E tilde is the energy contained in small scale. So d by dt of E tilde is changing due to this integration of this flux term. Pi tilde is the flux which is obtained by filtering the governing equation. So pi tilde tells us the rate at which small scales are getting energy from large scales. And so this is a representation of flux in physical space. So plotted here is a flux for the highest Rossby number case we looked at. So this is a normalized flux, the spatial structure of the normalized flux, and this is the histogram of the flux. And you see multiple striking things in this figure. The first thing is that this flux is it's almost symmetric. In fact, the positive tail is slightly higher than the negative one, but it's almost symmetric, which means the regions where flux is positive and negative, although on average, the mean denoted by this red dashed line, the mean is positive. So it's a forward flux. There's energy going to smaller scales, but it's almost symmetric, and the standard deviation of this curve is much higher than the mean. And to understand where this flux is located, we decompose this flow into this barotropic flow into strain dominant and vorticity dominant regions. So this is something many people in the oceanography community are familiar with. The Okubo-Rice criterion allows you to write a strain and vorticity, and you can identify regions where strain is higher and vorticity is higher. This is the barotropic flow for the highest Rossby number case that we looked at earlier, and this is the corresponding strain. Now, if you compare these two figures, you'll find that the strain rate has these holes in the center of these coherent structures. Everywhere there's a coherent vortex, you'll find these holes which correspond to low strain values. So the strain is very high near the vortex boundaries, in the peripheries of these vortices. These are regions where strain is very high, and strain is the lowest at the core of these vortices. So strain dominant regions are regions typically outside these coherent vortices, and vortex dominant regions are core of these vortices. And so when you look at these flux, if you compare these two figures, you'll find that in these regions where strain is very low, the center of these vortices, those regions where you see a hole here, you will actually see a hole in the flux plot as well. So we find that flux is high in strain dominant regions, and flux is very low in vortex dominant regions. So about 60 to 70% of the forward flux is based in strain dominant regions, and these happen to be regions right outside these coherent vortices. So a lot of the forward flux happen in the vortex peripheries. So as we increase Rossby number, the flux increases around the vortex peripheries, the forward flux, and that goes hand in hand with the vortices shrinking in size and reducing in number and disintegrating. So I'll make one more comment before I finish the talk. So one of the interesting results of this work is that, the amount of unbalanced energy level you need to disrupt balanced structures and break coherent vortices is really small when Rossby number is order 1. It's in contrast to Rossby's small regime, we need a lot of unbalanced flow or waves to cause this damage. And this is, I think this was very well noticed by Trish and Wood as this paper. So one of the things they do in this paper is they integrate the Boussinesq equations, and they keep track of the flow that's associated with the PV field, and everything else, everything that's not associated with the PV field, they filter off as a function of time. And when they do that, they find that even when Rossby number is order 1, they're able to find structures and properties of balanced flow and QG-like dynamics, even Rossby number is 1, provided you filter off things that don't project on PV. So we did a similar experiment where we took this model and as a function of time, we filter off the paraclinic flow, the unbalanced flow over time. And when we do that, so this is comparing the result of the experiment. So the top is the figure we already saw, paratropic flow at order 1 Rossby numbers with the paraclinic flow. Bottom is the case, similar Rossby number, high Rossby number, but we filter off the paraclinic flow gradually as a function of time. And with that, we still get these large coherent structures, inverse flux, and big vortices formed, domain scale vortices formed. So you really need a small unbalanced flow at order 1 Rossby numbers to cause a lot of this damage and enhance dissipation of the flow. And a small unbalanced flow can make a lot of difference at this order 1 Rossby number. So with that, I will conclude. Small Rossby, this is the first line is what's pretty well known from a lot of work that is known in this field. Rossby order 1 limit, you need unbalanced energy levels to be very high to impact and dissipate and disrupt coherent vortices and increase forward flux of balanced flow. But as Rossby number approaches 1, very small unbalanced energy levels can do a lot of damage to the coherent structures, and this increases monotonically. So as you increase Rossby number, even the lower unbalanced structures can do a lot of damage. We see that cyclonic, so these are properties that are pretty well known from motion model results and observations. Cyclonic vorticity structures persist. Anticyclonic vortices, due to multiple instabilities, they break up and form background soup. And a lot of the forward flux increases monotonically, and a lot of this is based in regions right outside coherent structures in the vortex peripheries, which are also regions where dissipation is high. So I think I'll stop there and take questions.